On September 15, 2017, one of humanity's most ambitious space missions came to an end. The Cassini spacecraft, after more than 13 years orbiting Saturn, was deliberately sent into the planet's atmosphere, burning up as it transmitted its final stream of data back to Earth. It was a controlled ending, planned, precise, and scientifically necessary. Cassini had already transformed our understanding of Saturn, revealing its storms, rings, moons, and hidden ocean worlds. Once its fuel ran low, NASA chose to dispose of it in a way that prevented any risk of contaminating Saturn's moons, some of which may potentially support life. At the time, scientists believed the mission had reached its natural conclusion. Cassini's data had been collected, analyzed, and archived. Its final images, captured during its descent between Saturn and its rings, were considered visually stunning, but scientifically routine. Just another final set of observations from a long, successful mission. And for a while, that's where the story ended. But science has a habit of reopening closed chapters. Years later, researchers began revisiting old planetary datasets with far more advanced computational tools than were available during the mission itself. Artificial intelligence systems had evolved dramatically. New models could detect patterns in noisy, incomplete, or visually corrupted data that traditional analysis methods would completely miss. Among the datasets selected for re-examination were Cassini's final transmissions, particularly the last imaging sequences captured during its descent. At first, nothing unusual stood out. The images still showed what scientists expected: swirling atmospheric bands, faint distortions from radiation, and the complex layering of Saturn's upper clouds. There was beauty in them, but no obvious mystery. Then AI-based enhancement tools were applied, not to interpret the images in a human sense, but to identify hidden structures within pixel-level variations. That's when something unexpected happened. Instead of simply cleaning up noise or sharpening details, the system began detecting repeating patterns embedded within the data. These patterns were not obvious shapes like storms or shadows. They appeared as subtle, structured arrangements, consistent across multiple frames and different camera angles. At first, researchers assumed it was an artifact of the algorithm. Machine learning systems are known to see patterns where none exist. It's a well-documented problem called overfitting or hallucinated structure detection. But the results did not disappear with repeated testing. In fact, they became more consistent. Independent runs of the same analysis revealed the same underlying structures. Even when the dataset was split, randomized, or processed through different models, similar patterns reappeared. That raised an uncomfortable question. Was the system discovering something real within the data, or was something about the data itself guiding the model toward a specific interpretation? As analysis deepened, the AI began to identify mathematical relationships embedded in the pixel arrangements. Certain distributions resembled known numerical sequences found throughout nature, ratios that appear in biological growth patterns, spiral formations, and physical systems under extreme pressure. This didn't automatically imply intelligence or communication. Nature is full of mathematical order. Snowflakes, hurricanes, and planetary atmospheres all follow physical laws that can produce repeating structures. Still, the consistency of these patterns across unrelated frames prompted further investigation. Some scientists suggested that Saturn's extreme atmospheric dynamics, its powerful winds, electromagnetic forces, and layered gas compositions, could naturally generate highly structured visual effects that only now, with modern tools, could be recognized. Others remained cautious, pointing out that advanced AI is especially prone to finding meaningful-looking structure in chaotic environments, even when none exists. But the most intriguing part of the analysis came from predictive modeling. After training on portions of the dataset, the AI system began anticipating where similar patterns might appear in unseen segments of the images. It was not merely describing what was already there. It was forecasting structure in data it had not yet processed. This behavior sparked debate among researchers. Some interpreted it as a sign that the model had learned underlying statistical rules of the dataset. Others saw it as evidence that there might be deeper consistency in the data than previously understood. Then came one of the most debated anomalies in the Cassini record. During the spacecraft's final moments, mission logs indicated that a full sequence of rapid-fire images should have been transmitted, around a dozen in total. However, when the dataset was reconstructed, one frame appeared missing or irreparably corrupted. Engineers confirmed that the transmission itself likely occurred. The issue seemed not to be with data collection, but with retrieval or decoding. Attempts to recover the missing frame from raw telemetry failed. The data existed, but it was unreadable, fragmented beyond standard reconstruction methods. Some researchers speculated it could have been a simple technical failure. Others noted that radiation interference near Saturn's atmosphere can heavily distort high-speed transmissions, especially during spacecraft descent. Still, the coincidence of a missing frame in the most critical moment of the mission added fuel to speculation, even if no evidence suggested anything unusual beyond technical limitations. As these discussions continued, public attention briefly turned toward the findings, often amplifying them beyond their scientific meaning. Online interpretations ranged from misunderstood physics to imaginative claims about hidden signals or unknown intelligence. Within the scientific community, however, the consensus remained cautious. No verified evidence has shown that Cassini recorded anything artificial or intentional within Saturn's atmosphere. The anomalies, while interesting, do not currently exceed the threshold required to challenge established planetary science. But the broader impact of the reanalysis has been significant. It highlighted how much hidden information may exist inside old scientific datasets, information that was never fully extracted because the tools to see it did not exist at the time. It also raised deeper questions about how modern artificial intelligence should be used in scientific discovery. Is AI simply a better microscope for data we already understand? Or is it beginning to reveal structures in nature that we have never been able to perceive before? Cassini's mission, in this sense, remains unfinished, not because the spacecraft failed, but because interpretation continues to evolve. Its final descent into Saturn was never just an ending. It became a data-rich moment frozen in time, waiting for future generations to examine it with sharper tools and different perspectives. Whether the patterns found in those final images represent natural atmospheric complexity, limitations of AI interpretation, or something not yet fully understood, one thing is clear. The universe often appears simple at first glance. But when observed with greater precision, it becomes increasingly layered, complex, and open to interpretation. And sometimes what we think we have already understood may only be the beginning of a much longer investigation. Cassini may have stopped transmitting in 2017. But the questions it left behind are still being explored today.